what if our region is not polygonal? Okay, so the standard one would be the area of a circle. And the area of a circle, or the formula for the area of a circle, has been worked out a long time ago. It's not something new. But how did they do it? Because it's not polygonal, we cannot rely on the formula for a triangle. Or can we? Okay. The idea that the ancient Greeks had was as follows. First of all, they said, okay, let's make an approximation. If we can't do something exactly, we'll do it approximately. The way we're going to approximate it is we're going to say, all right, let's divide this circle into a whole bunch of circular sectors. So imagine that each one of these red segments goes from the center to the circumference, and they all go in equal angles. Okay. And now let's consider the straight segments that join the end of all those radii. So each one, also assume that each one of those little straight segments has length b, okay? B for base. Notice that what we've actually done is we have now described the area of a circle approximately as being made up of triangles. Each one of these triangles will have as base b, and its height is going to be, well, r, not quite r, but we're going to be very close, right? So approximately, remember we're doing approximations here, approximately we can say that the area of the circle is going to be equal to, approximately equal to n times, where n is the number of these triangles that we have constructed, and then the area of each triangle is going to be 1/2 base b times radius r. Again, this is not quite exact, it's approximate. But we can work with this approximation. Approximations are nothing new to us. So let's clean up that notation a little bit, and we end up with nb over 2 times r. Now, nb, if you think about it, is almost the length of the circumference of the circle, right? So we can write that formula as being approximately c over 2 times r. Now, if what I do is I let n go to infinity, in other words, what I'm doing is I'm going to construct more and more of these triangles. I'm going to divide the circle in more and more of these little thinner and thinner triangles. Then, of course, that approximation in the limit is going to become an inequality, because any space for the approximations will go away. Those blue segments are going to be not only approximately along the circumference, but as n goes to infinity, they'll be on the circumference. So if we do that, then A is going to end up being exactly equal to CR over 2, and C, by definition of the number pi, is going to be equal to 2 pi r, and here we get our familiar formula pi r squared. Now, this is a method that the ancients knew a long time ago. Again, we're talking about ancient Greeks, Pythagoras and his friends. And they called this method, actually it wasn't Pythagoras, it was someone else, but about that era. They called this method the method of exhaustion, because they were exhausting every little piece of the circle by letting n go to infinity. They came this close to the idea of a limit, and they did not realize that. Had they done that, probably mathematics would have developed a lot faster. But hey, you can change history, so here we go. What we're going to do now is we're going to use something similar to this idea of exhaustion, the method of exhaustion, but by using limits. Okay, we're not going to look at limits in this class. We're going to look at that in the next class, but we're going to set up the groundwork. Let's see how that works. So we're now going to try and figure out how to compute the area of a region whose boundary is not made up just of straight segments, but has some curved part in it. We're going to start very simple. So we're going to start on the xy plane, and on this xy plane we're going to make some even more simplifying assumptions. For instance, we're going to look at a region whose bottom is straight and it's along the x-axis. Also, we're going to assume that the top is going to be some positive function, so it looks like that. And we're going to assume that the left and the right sides are going to be straight vertical segments. So if you think about it, this is pretty much a rectangle. The only thing it's missing is that the top is not straight horizontal, but is some kind of curve. Okay, so we're almost there, but we're assuming that just one side of it is has become curved. So let's see what we can do with it. What we can do, just like what the ancient Greeks did with the circle, is try to approximate this region, the area of this region. But instead of using triangles, we're going to use rectangles. So what we're going to do is we're going to use very thin rectangles. Okay, so what I'm going to do is I'm going to draw thin rectangles, each of which is going to approximate the corresponding portion of the region. And I'm just drawing some of these rectangles. You can draw as many as you want. Okay. Then what happens is that the area of the region I'm looking for is approximately going to be equal to the sum of the areas of those rectangles, each of which is going to be made up of a base and a height. So for the first rectangle is B1H1, the second one is B2H2, etc., etc. You're going to end up with the sum of all of those. If we want to use the short sigma notation, we can write the area is approximately equal to the sum from 1 to n of BI/HI. Now notice, however, that each one of those HI's, I drew it in such a way that the height of each rectangle corresponded to the height of the function somewhere, either here or here or here, or well, this one I went a little bit overboard, didn't I? Okay, so it should have been a little bit smaller. Okay, unless we want to consider this one as being the point. Okay, and this one the same thing, and so on. Right. So for each of these rectangles, what happens is that the height of the rectangle is going to be the value of the function at some x value. All right. So what we're going to do is we are going to write. Oh, right, yeah, this is the even shorter notation, okay? Because the end is really not going to play a big role for a while, I'm just going to drop it. I'm going to assume I know that we have n of these rectangles, so I'm going to just write the total area approximately as the sum of BI/HI or the sum of BI/f of xi. Okay. So if you're not quite sure about what this notation means, please pause or rewind and look at it again, because you don't want to just read those letters and have no clue what you're reading. You want to make sure that as you're reading them, you're visualizing in your mind what each of those pieces actually means. Now, if we want to get a better approximation with this method, all we have to do is increase n. And you can already start thinking, now that we know about limits, that we could actually use limits to get the exact value of that area. We're going to do that next time. Hold on to your hat. So I just want to clarify a few more things first. Okay. Now also, in order to keep things simple, we're going to use strips of equal width. So what we're going to do is we're going to assume that each one of those bases is going to be equal to the total width of our region divided by how many segments we have, and this is pretty much what we used to call delta x. It's just a little horizontal increment. Okay, so we're making lots of simplifications so that we can get down to just the concept and understanding what we're doing without having to worry about too many details.